Hello, and welcome to my talk on the effects of a non-symmetric slight contraction on a turbulent flow produced by an active grid. So the motivation behind this is really trying to understand turbulent inflow and its effect on wake swirl. So where does wake swirl actually happen? One example in industry is a wind turbine extracts energy from the flow and imparts torque onto the flow, so that the wake actually has a large-scale net rotation that we call a swirl. So the approach to understand that is, one, how do we create that in the wind tunnel setting? And you can do that with something called an active grid. So if you look at the little caricature on the right, you have your active grid here, and I'll explain exactly how it produces turbulent inflows, but essentially it parts of vorticity in the flow, and as it enters into your test section, that flow eventually cascades down into heat in the typical sense of turbulence, so that then by way of the active grid, you can change these quantities to match something that would resemble, let's say, free space turbulence that happens in the atmospheric boundary layer. So in my particular situation, placement of the grid was critical, as the UW's Aeronautical Laboratory has a very short test section, about 4 feet. So the worry is this breakdown may happen towards the aft end of the test section, which would really undermine wake studies in the test section. So exactly what an active grid is, well, an active grid was first published in literature by Makita and Sasa in 1991, and they used it to essentially change turbulent inflow quantities. So a grid, and you'll see in this video, is essentially a grid with control surfaces that are actively driven by the actuation of motors. And so this is looking through the test section up into where our active grid is placed, and you can see, if I pause it quickly, that each adjacent row is essentially out of phase with each other. This is a mode that we would call a constant blockage mode, and it's all driven, in this case, at 1 Hertz frequency. Also notice in this video that the active grid is not placed at the beginning of the test section, but actually just forward of a contraction. And the reasoning for this is a slight contraction improves isometry and essentially conditions the flow. That was first demonstrated by Kumbalot and Corson in 1966 for a passive grid. And then later on, Larson and Davenport, the only study in 2011 to show that an active grid also with the slight contraction produces isotropic flow. So I'm going to, in this talk, demonstrate the capability in turbulent inflows produced by the active grid contraction configuration, specifically for non-symmetric contraction. And the approach to do that is I'm going to measure the flow with constant temperature anemometry. I'm going to use that to assess the turbulent kinetic energy throughout the test contraction. I'm going to dissect that, and look at the normal Reynolds stresses, and then dissect those further by looking at the frequencies that contribute to them through the autospectral density function. I'm kind of give you some orientation. This image on the right is of the open loop wind tunnel facility at UW, and you can see that this contraction leads right to the placement of the grid, and then there's a secondary contraction in the test section. This current configuration is in the laminar version of the tunnel with the grid stowed below. So the wind tunnel, again, is an open loop, low speed, 0 to 45 meters per second with a 61 by 61 centimeter squared cross section. Traversing the hot wire probe was done by an in-house 4 degree of freedom traverse system, as you can see here on the right. The active grid is a 102 by 71 cross-section active grid with 240 chevrons or control surfaces that are driven by 40 axes. And the contraction here is a slight contraction of 1 to 1.96, and kind of denote that it contracts more in this direction than it does in the vertical direction. And so the specific hot wire that I chose to use was an X wire with a 5-micron tungsten wire. It was controlled by an AA Labs 1003 chassis. The flow was the temperature of the flow was needed to be measured to correct for thermal drift for hot wires. Did that with a Type K thermocouple. The signal was filtered at 100 kilohertz and with a cutoff frequency of 43 kilohertz with a low pass 6-pole elliptical filter. The signal then was digitized on an NI PXI 6123 card. And then further, the signal was decimated down to 20 kilohertz using an 8th order Chebyshev IR filter. Record lengths were at 10.2 seconds, and this was to ensure at least a resolution and spectrum to be 1/10 of a hertz. So now I'm going to orient you to the coordinate system. So this image on the right is of the active grid in contraction system, and the coordinate system is grid-centric, and it's in a left-handed sense. And so all the measurements that I will demonstrate today or show today have been done along the x-axis here, and they start at about halfway through the contraction and end at the beginning of the test section. And the reasoning for that is halfway through, as you approach closer and closer to the grid, terms of intensity becomes so high that the belief in hot wire measurements is of question. So without further ado, we're going to look at just use quickly some dimensional analysis to help create some test conditions. And since the components of the normal stress, Reynolds stresses of concern, they take of this form, and using some of the parameters for the grid and the contraction, you end up getting 4 pi groups. One is actually a ratio of Reynolds to Struhel number, and Reynolds G represents the grid, so it's the velocity at the grid with a length of representative of one of the chevrons. The Struhel number is again the velocity at the grid, but with frequency f, which is the driver frequency of the grid. And then there's this 4th parameter that drops out, du dx over f, which is similar to a Struhel number, and is basically the ratio of frequency input of, let's say, a fluid particle being accelerated through the contraction to the ratio of the frequency being frequency of the grid. And so the test sections that came out here were picked to demonstrate at least the bounds of TKE we could see in the flow. And so for test 1, the grid was not driven at any frequency. It was held fixed at a certain blockage ratio of 7%. And then the test 2 was the grid was run at 1 hertz at a constant blockage of 50%, which is actually the mode you saw earlier in the video. So now we're going to look at the TKE and how it evolved through the test section or contraction. So if you look at the image on the right, the blue is corresponding with test case 1, and the red is corresponding with test case 2. So again, red is active, blue is passive. And the big takeaway from here is you can see that through the actuation of the grid, we're injecting energy into the flow, and that as expected, we can see that the flow does decrease, or the energy does decrease monotonically throughout the contraction. So now we want to dissect the TKE further. So we're going to look at the normal Reynolds stresses. And so I'll take your attention to these 3 curves at the bottom of the chart on the right. Blue is related to WW, black is related to UU, and red is related to VV. And you can see in the passive case, and this is related to the passive case, that all components decrease monotonically. But contrary to what we see in the active case, we can see that UU dominates initially and then quickly decreases monotonically, while WW behaves a little bit differently, and towards, the quarter way through, it looks like it begins to dominate with WW over UU, and this might be an indication that there's an energy transfer between that component. But you can see that in both cases, the Reynolds stress, normal Reynolds stress components become equivalent towards the end of the contraction. And so if we look at their RMS ratios for both test cases, we relatively reach an isotropic state towards the end of the contraction. So now further, we're going to dissect those components by just briefly looking at SWW. And SWW is just representative of SUU. They all essentially had the same shape and they had the same behavior. So we're going to look at first active and passive. And so blue here is for the passive case, and then red again is for the active case. And you can see that for the active case, we're able to inject energy at these larger scales or slower frequencies, and noting that 1 hertz is the driving frequency of the grid, and you do see that. And these locations are just at the end of the contraction. Also, we kind of just want to see how the spectrum or these frequencies evolve through the contraction. So you take your attention to the right image. The blue, this is for active case, but the blue color is actually as far forward as we can go in the contraction, the red is, and the blue is right at the end of the contraction. And you can see in the red case, we kind of have a piling up of energies at 100 hertz, but as we get to the end of the contraction, you see that that energy has washed out, and then we're able to get a negative 5/3 slope, which is indicative of inertial subrange. So in summary, the active grid contraction configuration demonstrated the ability to inject energy into the TKE of various levels, and it's allowed the flow to evolve into an isotropic state with fewer artifacts in the spectrum by the time it reaches the test section. And I'd like to conclude that an active grid contraction configuration is actually a favorable configuration for small wind tunnel facilities to produce these types of flow, so that they can take and utilize their whole test section for turbulent inflow experimentation, which then would make them more competitive with larger wind tunnels. To kind of continue the characterization of this flow, the next step is to do 2-point crosswire measurements to characterize length scales of the flow. And once that is completed, we'll use that as a test bed for inflow to emulate free stream turbulence, so that then a study can be done to see that effect on the evolution of wakes with swirl. We're excited. And I'd like to acknowledge support, the Department of Energy supporting this this work. And I appreciate your time.